Hi, thanks for joining me. Today I've got a really interesting problem to do with this huge number here. 3 plus root 17 over 2 to the 2023 plus 3 minus root 17 over 2 to the 2023. It turns out that this number here is an integer. The question is it odd or is it even? So firstly, the fact that this is even an integer I think is pretty remarkable, but the fact that we can also tell whether it's odd or even without doing any difficult calculations is actually pretty impressive. Do have a go at this problem, but I'm going to dive straight into a solution. Okay, so the way that we're going to solve this problem is kind of just by ignoring this 2023 and replacing it with a general number n, and then at the end we'll think about what happens when n is 2023. Okay, well what I'm going to do first is just call this number here a, so 3 plus root 17 over 2 I'm going to call a, and this guy here I'm going to call b. And so we're interested in a to the n plus b to the n. And now what we're going to first do with this expression is kind of write this as a plus b times a to the n minus 1 plus b to the n minus 1. But of course, these two things aren't quite exactly the same because yes, a times a to the n minus 1 gives us that term, and b times b to the n minus 1 gives us that term. We're still left with these extra terms, so a b to the n minus 1, so let me subtract that off, and b times a to the n minus 1, let me subtract that off as well. Okay, so let's just neaten this out. We get a plus b times a to the n minus 1 plus b to the n minus 1. And then we're subtracting off these two terms, but both of these terms here have both an a and a b in them, so I may as well factor that out. And if I do that here, I'm left with b to the n minus 2. And this one, I'm left with a to the n minus 2. Maybe you can have a sense of where this is going. Right, let's look at this a plus b here. Well, we can work out what that is because we know what a is and we know what b is. If I do a plus b, that's simply going to be 3 plus root 17 over 2 plus 3 minus root 17 over 2. And the root 17s will cancel and I'll just get 6 over 2, which is 3. So this will be 3 times a to the n minus 1 plus b to the n minus 1. Okay, what about a times b? Well, again, I can just work that out. A times b here, what would that be? That's going to be 3 plus root 17 times 3 minus root 17, all over 2 times 2, which is 4. Now the numerator is just the difference of 2 squared. I get 9 minus 17, which is going to be minus 8 over 4, which is minus 2. And so this minus ab term is going to become minus 2, so plus 2, and then I've got a to the n minus 2 plus b to the n minus 2, like so. Cool, so we've expressed a to the n plus b to the n in terms of a to the n minus 1 plus b to the n minus 1, and a to the n minus 2 plus b to the n minus 2. This looks quite nice. What I'm going to do, just to make this explicitly clear, is just call f of n a to the n plus b to the n. And so what do we have? We have a nice little recurrence relation here. F of n is 3 lots of f of n minus 1 plus 2 lots of f of n minus 2, like so. And so we can write the next term in our sequence in terms of the previous two, a bit like with Fibonacci numbers. Okay, cool. So let's actually work out a couple of terms in this sequence. Let's work out what f of 0 is. Well, that's just going to be a to the 0 plus b to the 0, which is 2. That's nice and straightforward because any number to the power of 0 is 1. Okay, what about f of 1? Well, that's a plus b, and we already worked that out over here. That's 6. 6 over 2, which is 3. Cool. And now, just to get any other term in the sequence, we can just use this recurrence relation we've got here. So f of 2 is going to be 3 lots of f of 1, which will be 3 lots of 3, so 9, plus 2 lots of 2. So that's going to be 13 here. So 9 plus 4 is 13, and we get, f of 2 is 13. And well, hopefully you can see that now every single number I generate will also be odd, because if I do the next number in the sequence, f of 3, let's say, it's going to be 3 lots of the previous one, which was 13, and that's therefore going to be odd, plus 2 lots of something. And this thing here is always going to be even because of the 2 there. So realistically, to determine the parity of f of n, I only need to focus on this first term. And just by induction here, if the previous term is odd, that means that the next term will be odd. And we can just proceed by induction here. Since f of 1 is odd, that means f of 2 is odd, f of 3 is odd, f of 4 is odd, and so on. And so in particular, when I plug in n is 2023, it will be odd. And so we get that 3 plus root 17 over 2 to the 2023 plus 3 minus root 17 over 2 to the 2023 is an odd number. And we didn't have to do any difficult calculations or expansions or anything like that of this guy. I think this is a pretty neat problem and a nice little introduction to deducing recurrence relations on things like this. So if you've not seen the if you've not seen the explicit formula for the nth term of a Fibonacci number, of the Fibonacci sequence, I'd encourage you to have a look at that, because we're all familiar with the recurrence relation of the Fibonacci numbers, but it turns out there's a nice little explicit formula. It looks a little bit like this, but involves the golden ratio. So that's a really, really interesting area of maths, which I encourage you to have a look at. Anyway, I will finish there for today. Thank you for watching. I'll catch you in the next one. Have a great day.